Good evening, everyone. We're starting chapter 6. As we did with previous chapters, we haven't finished the full set of sections in the labs in the previous chapter, in the cross-validation and bootstrap chapter. We'll probably do a session later on where we'll maybe take 2 or 3 days and we'll consecutively and we'll go over the labs just as a revision when it comes to R and just the main concepts. But let's look at what we're doing in these next few days. We have linear model selection, and this is quite a long word, but it's regularization. Let's see. In the regression setting, and do remember, regression as opposed to classification. In classification, it is qualitative factors such as drug overdose, stroke, and seizure. In regression, you're predicting a variable that takes on numerical, so quantitative values. In the regression setting, the standard linear model, so we're still working under the assumption of linearity with these terms as a function of the predictor variables from 1 to p. You'll always have an additional term due to the intercept term, together with an error term, and just think of that error term, epsilon, reflecting the limitation of the model in terms of, one, how good that linearity assumption even is, and two, any predictor variables that haven't been considered, any variables that are relevant to y, that do have an impact on y, but for whatever reason, maybe we didn't have the data for these variables, maybe we had it, but it wasn't too trustworthy, or maybe we just didn't notice how important it is, weren't considered in the pink expression over there. And this formulation is commonly used to describe the relationship between response y, a numerical response y, and a set of variables x1 until xp. We have seen in chapter 3 that one typically fits this model using least squares. What does least squares aim to do? It minimizes the mean square error based on the training set data, based on the observations that you're feeding the modeling process when you're calculating those parameters from beta naught to beta p. In the chapters that follow, okay, so this is plural, we consider some approaches for extending the linear model framework. So we're going to go beyond linearity now. In chapter 7, we generalize 6.1 in order to accommodate nonlinear, but still additive relationships. And I would imagine by additive, we simply mean that we are adding the influence of each predictor variable on y, while in chapter 8, we consider even more general nonlinear models. So I guess not necessarily additive. However, the linear model has distinct advantages in terms of inference, and on real problems is often surprisingly competitive. We'll see what we mean by competitive. Really just means minimizing, for instance, the test mean square error in relation to nonlinear methods. Hence, before moving to the nonlinear world, we discuss in this chapter some ways in which the simple linear model can be improved by replacing plain least squares fitting, oh, interesting, with some alternative fitting procedures. So this is a chapter where we still keep the linearity assumption between the predictor variables and the response variable, y. We will not necessarily parameterize, meaning we will not necessarily estimate the beta parameters using least squares. Why might we want to use another fitting procedure instead of least squares? As we will see, alternative fitting procedures can yield better prediction accuracy and model interpretability. Remember, when we speak of accuracy, usually what we have in mind is actual versus expected. And we're going to go into some more detail, prediction accuracy, provided that the true relationship between the response and the predictors is approximately linear, the least squares estimates will have low bias. Now, this is a word that does come up occasionally in the book, but what do we mean by bias? Well, the first time we encountered bias was in the bias variance trade-off, which we had seen in chapter 2. Let's find it over here. And do we have a diagram that quickly gives us? So the blue curve is bias, is measuring bias. Let's see. What was bias? What was bias? Right. So mean square error, or the expected mean square error, your actual less expected all squared, you may decompose it into these three terms. You don't have much control on the variance of epsilon. Can't really do much about the error term, but you would pick a model that tries to minimize the variance of the model and the bias of the model. Now, what do we mean by, here we go. Variance refers to the amount by which the model, so the parameters, which are in many ways being collected under this object f hat, would change if we estimated it using a different training data set. So a model's variance is just how sensitive the parameters are to using a different set of observations. Now, the bias refers to the error that is introduced by approximating a real-life problem by a much simpler model. Okay. So as we use more flexible methods, the variance will increase. Yeah. So if you use a more flexible method, like the green model, remember, when you fit a curve, think of it as a model. So the more flexible you allow your model to behave, to reflect your specific training data, if you use the different set of observations, even a single data point can have perhaps I'm looking for a word that starts with over. Um, it would have an overly mm, it would have, what's the word I'm after? Mm, when you when something's a lot greater than it should be, like a disproportionate. So even a single data point could have a disproportionate impact on the overall model. So the more flexible you allow your model, the more variability there is within it. And you don't want that. You want to minimize the variability. Mm-hmm. On the flip side, the bias will decrease. So the more flexible a method is, I think this is how we should think of variance and bias within a model. The more flexible a method is, so think of from these three models, I say three because the black is the true relationship. As always, we're playing God over here. So you know the true relationship. The fitted models are the green, the blue, and the orange. And the more flexible we allow our model, the higher the more flexibility we allow within our model, then the higher the variance, but the lower the bias. So what is bias? Bias is, I think we can think of it as sort of um, the extent of simplifying the model. So the more flexible a method is, a fit is, the higher the variance, but the lower the bias. The relative rate of change of these two quantities determines whether the test MSE increases or decreases. Okay, so I think that was some much needed revision for all of us here. Now, going back to chapter 6, let's see if we can make sense of this. So the prediction accuracy, provided that the true relationship between, right, provided that the true relationship between the response and the predictors is approximately linear, well, then the least squares estimates will have a low bias. So the assumption of linearity is a good one, quote unquote. So using least squares, which gives you these linear fits, will result in a low bias. If the number of observations, so you're using in the auto data set, we have around 392 observations. Double inequality means is much greater than. Yeah, mathematically, what do we mean by much greater than? Depends on the context, but let's just go with it. If the number of observations is much greater than, significantly greater than, the number of predictor variables, that is, if n, the number of observations is much larger than p, the number of predictor variables, then the least squares estimates tend to also have low variance, and hence will perform well on test observations. So up to this point, this is where you would use these squares. Using these squares, if these two conditions are met, and I'm referring to which two conditions, that the true relationship between the response and the predictors really is basically linear, and if the number of observations that you have available within your training data set is significantly greater than the number of predictor variables, then you're going to have a low bias and a low variance, which is exactly what we want to get to a low mean squared error. Mean squared error. Actual minus expected, everything squared. Now, is this always the case? Well, no, probably isn't always the case, right? In fact, we're going to go on to read, however, if n is not much larger than p, then there can be a lot of variability in the least squares fit, resulting in overfitting and consequently poor predictions on future observations not used in model training. So that's the test mean squared error, not used in the model training. Even worse, if the number of predictor variables is greater than the observations, then there is no longer a unique least squares coefficient estimate. The variance is infinite, so the method cannot be used at all. By constraining or shrinking the estimated coefficients, so taking a lower value of p, so by just ignoring some of them, we can often substantially reduce the variance. That's what we want, right? You want to reduce the variance at the cost of a negligible increase in bias. And variance and bias are often mentioned in the same sentence due to this trade-off in all of statistical learning. This can lead to substantial improvements in the accuracy with which we can predict the response for observations not used in model training. Okay, so that's the first point to consider. This point being the prediction accuracy. One would hope that the model, our fitted model, does a good job on average in predicting future outcomes. In fact, very often models are justified practically entirely on the predictions that they make. If the predictions don't make sense, then it's maybe time. If the predictions that the model makes are really far off from the actual data, then maybe it's time to ditch the model, or definitely to take a closer look at it. Model interpretability. In data science, and actuarial science is no exception, we often speak of a black box where certain models are either black boxes, you don't really know what's going on in them, or they're treated as black boxes. I would imagine interpretability has to do with that kind of idea. Let's see. It is often the case that some or many of the variables used in a multiple regression model are in fact not associated with the response. This should remind you of the null hypothesis. Including such irrelevant variables leads to unnecessary complexity in the resulting model. By removing these variables, that is, by setting the corresponding coefficient estimates to 0, we can obtain a model that is more easily interpreted. Now, least squares is extremely unlikely to yield any coefficient estimates that are exactly 0, right? If we go into R, and we have quite a few tabs now at this point, but we could take the one where we had on horsepower squared. I'm going to going to run it over there. And if we look at the parameters, it's very rare to get exactly 0, even if the p-value is high enough that you'd actually say, okay, this variable that doesn't really help me, doesn't really knowing this variable doesn't really add to the likelihood of correctly predicting the output. So we can forget about least squares doing this job for us of telling us, hey, listen, ignore this specific predictor variable. In this chapter, we see some approaches for automatically performing feature selection, also known as variable selection, that is, for excluding irrelevant variables from a multiple regression model. Okay, there are many alternatives, both classical and modern. Alternatives to what? To using least squares to fit this expression. In this chapter, we discuss 3 important classes of methods. Subset selection. This approach involves identifying a subset of the P predictors that we believe to be related to the response. We then fit a model using these squares on the reduced set of variables. So you're still using these squares, but there's a step before that where you actually might decide to exclude some of the predictor variables available to you from the data set. So although you're using these squares, this approach isn't considered a pure least squares because you're actually excluding, or you might exclude certain predictor variables. Shrinkage. This approach involves fitting a model involving all P predictors. However, the estimated coefficients are shrunken towards 0 relative to the least squares estimates. This shrinkage, also known as regularization, has the effect of reducing variance. Depending on what type of shrinkage is performed, some of the coefficients may be estimated to exactly 0. Hence, shrinkage methods can also form variable selection. Okay, so in many ways, it kind of comes similar to subset selection. Dimension reduction. This approach involves projecting the P predictors into an M dimensional subspace where M is less than P. Interesting. This is achieved by computing M different linear combinations or projections of the variables. Then these M projections are used as predictors to fit a linear regression model by least squares. Okay, let's see. In the following sections, we describe each of these approaches in greater detail, along with any advantages and disadvantages, although this chapter describes extensions and modifications to the linear model for regression seen in chapter 3, the same concepts apply to other methods, such as classification models seen in chapter 4. Okay. Subset selection. In this section, we consider some methods for selecting subsets of predictors. These include best subset, and stepwise model selection procedures. Okay, I'm going to start with best subset selection. To perform best subset selection, we perform a separate least squares regression for each possible combination of P predictors. That is, we fit all P models that contain exactly one predictor, all P choose to models that contain exactly two predictors. This is Pascal's triangle, isn't it? So Pascal's triangle, I probably don't have a Word file open. I actually do. Pascal's triangle is that array. Let's do one very quickly. These are binomial coefficients where you get 1, 1, 1, 1, 3, 1, 1, 4, 4, 1. Can delete these for the time being. So Shift F10, delete, and delete the entire row. We'll turn these into mathematical notation using equation editor. Remove the border, Alt H B N, and if I do Alt J L and W, we can specify the width. So for example, 1.5 centimeters, and finally Alt HC. Okay, so how does besides the fact that I don't even know the first few entries of Pascal's triangle, so that's probably a bit better. How does this work? So let's say that we have. I wouldn't be surprised if this is wrong as well, but we have, let's say we have a model with P equals 3. So the data set that we have available has 4 columns. 3 columns may be taken as the predictor variables, and the 4th column is the response. Now, do I need to take all 3? I could, and there's exactly one way of doing that. There's one way of choosing 3 from 3. That's 3C3, 3 choose 3, and that's 1. Of course, I could only select 2 of these 3, and that would be 3 choose 2, which does give you 3. You could choose 3, you could take 3, but only take 1. So just the first predictor variable, or just the second predictor variable, or just the third predictor variable. And of course, the most extreme case is you pick none of them. So that would be the null model, maybe. Oh, incidentally, and I'm sure you know this from other subjects. If you add these, you would get, for example, 2 to the power of 3, which is 8. That is simply a result of what? Well, it's a result of the number of subsets. So let's say I had predictor 1, predictor 2, predictor 3. This set has 3 elements, so it will have 2. So if this is set X, this set X, how many subsets does set X have? So it will be 2, assuming this is finite, 2 to the power of X, Y. 1, 2, 3, 4, 5, 6, 7, and the 8th subset is the empty set. Every set has the empty set as one of its subsets. So you're going to perform this fit how many times? Well, it will be 2 to the power of p, right? Just like we said, 2 cubed. We then look at all of the resulting models with the goal of identifying the one that is best. So if you have three predictor variables, you're going to create 8 models. And then, for example, you'll compare their mean squared error, and that would be maybe the best model. The problem of selecting the best model from among the 2 to the power of p possibilities considered by best subset selection is not trivial. This is usually broken up into 2 stages, as described in algorithm 6.1. And we start with the empty set scenario. Let M naught denote the null model which contains no predictors. This model simply predicts the sample mean for each observation. Sample mean for each observation. I'm not entirely sure I know what that means. So from your data, you're going to exclude, if this is your data set, you're going to exclude everything with the exception of the response variable, right? You're going to exclude all the characteristics, x1, x2, up to xp, and you're only going to look at the responses. The sample mean for each observation. The sample mean, do they mean the sample mean of the observations? I think you just calculate the mean. Just calculate the mean of these y's, and that's your model. Your model just tells you, listen, I'm not going to look at the characteristics. 2 patients could have very different symptoms, and I don't care. I'm just going to tell you both of them are seizure, because we had a lot of seizures last week. And then going by last week's data, ignoring the symptoms among patients, most of them had a seizure. So I'm just going to say, whatever input you give me, I'm just going to tell you seizure. So that's a null model. That's a null model, which is better than nothing. One hopes to improve on it using the actual predictor variables. Now, for k equals 1 until p, fit all p choose k models that contain exactly k predictors. Okay, so all it's telling us is, and please do ask me to repeat when necessary. Not that you need my repetition, I'm sure, but whenever you get distracted or whatever, do let me know. So for example, let's take when k is 1. So when k is 1, you'll have p choose 1. So you'd have p models. You'd have p of them. The first model would just take the first predictor variable, x1. The second model would, they would all be simple linear regressions. I usually mention Hooke's law, where you just have the extension regressed on the load. Okay, and each of these models contains exactly k predictors. So for example, 1 predictor. Each of these p models contains 1 predictor. Okay, now you pick the best among these p choose k models, and you call it mk. Here, best is defined as having the smallest, what was this? Residual sum of squares, or equivalently, the largest R squared, which we've tried to avoid for the time being until now. Select a single best model among M0 to MP using cross-validated prediction error. So we could use chapter 5. We could use the Akaki information criterion. There's a BIC, I think that's Bayesian information criterion, or adjusted R squared. We don't need to know the specificities of each sort of measurement, cross validation or whatever. But the idea is just to get a feel of how the process is going to work. So you fit all the models with one predictor and you pick the best one. You then fit all the models, each one with 2 predictors, and you pick the best one. So I suppose we're going to use linear regression, right? When we say fit, there's going to be a linear regression. I mean a least squares prediction. I'm all over the place. A least squares fit. We do remember what least squares are, right? You are reducing it's the residuals, right? Let's see. Oopsie. Here you go. These squares minimizes the RSS. It is the difference between actual and expected squared for each observation, and you sum. Okay. Let's go back to chapter 6, which is, I think, over here. In algorithm 6.1, step 2 identifies the best model on the training data for each subset size in order to reduce the problem from 1 of 2 to the p possible models to 1 of p plus 1 models. What are we saying over here? These are your p plus 1. There are p plus 1 because of that 0 models. We're just going to have these battling it out between each other. There'll be M0 with no predictor variables. M1, it is the best model with a single predictor variable. M2, the same thing until MP. Of course, MP is just least squares. MP is all the predictor variables. In fact, pick the best, M0 and MP. You already know that M0, that's just going to be the null model. There's only one of them. It's the ones in Pascal's triangle. There is no fighting over here, but there will be a competition over here. So you pick the best among these 3. You pick the best among these 3, for instance. In figure 6.1, these models form the lower frontier depicted in red. What was that? In figure 6.1, these models form the model frontier predicted in red. Predicted in red. Oh yeah, think I know what it's doing. I think I know what it's doing. So, for example, you have all your models using 6 predictors. I don't know, the first 6, the last 6, middle 6, the first 3 and the last 3. And one of them has the lowest residual sum of squares. So you pick that one, you pick the model that gives you this one for your M6. So M naught gives you this. Although I don't know why there are these. I wasn't expecting those. There is only one M naught. Or is this one? Okay, so have they left 0 out? Okay, maybe they've left 0 out. So okay, so these are all the models with just a single predictor. This is the best one from the lot. This is the best one from the models that only take 2, models that take 3, models that take 4, that take 5 predictors, etc., etc. And this would appear to be 2 sides of the same coin. You either reduce the residual sum of squares or you reduce R squared. For each possible model containing a subset of the 10 predictors in the credit dataset, the residual sum of squares and R squared are displayed. The red frontier tracks the best model for a given number of predictors according to RSS, which apparently you want to minimize the RSS, which we know. We've been discussing this for many weeks now. So I should have used the word apparently, just because we haven't really delved into too much detail concerning R squared. Now I say apparently you want to maximize R squared. So we all have a very good understanding of targeting the minimum residual sum of squares. R squared you want to maximize. Though the data set contains only 10 predictors, the x-axis ranges from 1 to 11. Since one of the variables is categorical and takes on 3 values, leading to the creation of 2 dummy variables. Interesting, right? Do you remember the credit dataset? This? Was it the races? Was it the races of the borrowers? Is that the categorical? Yes, right? This is a... Oh, I see, I see. So even gender, student, and married are categorical, but since gender is 2 levels, you for example say 0 male, 1 female. So all you encode is the 1. If you see a 1, then it's a female. If you see a 0, but that's a single dimension. Whereas ethnicity, you have to sort of create 2 dummy variables. To be African American, yes, no. And for instance, Asian, yes, no. You can leave the third one out because if it's no for African American and it's no for Asian, then automatically you conclude that the borrower is Caucasian. So this is why. If I go back into R and we look at the structure, although it was 12 variables, you exclude the one, you exclude the default, not the default, you exclude the response. And what was the response? Was it, what were we trying to predict? What were we trying to predict in the credit? I can't remember. Let's say we're trying to predict balance. So now you're here you would take these 11. Yeah, but 1 second. The book says why does the book say though the dataset contains only 10 predictors? Does it contain 10 predictors? Oh, maybe ID isn't a predictor. Maybe ID is just, yeah. I mean, ID is nothing, is it? It's just giving you the row number. So that's what they're referring to over here. You only have these 10 predictors. That's the maximum number of predictors that we can take. But ethnicity, being categorical with 3 levels, is going to contribute not 1, but 2 predictor variables. For instance, African American, yes, no. Asian, yes, no. Of course, you can't have a 1 in both of them. You can't have African American, yes, and Asian, yes, as well. Leading to the creation of 2 dummy variables. Okay, which is why we have 11. Which is why we have 11. Notice that for the model with 11 predictor variables, there are no other models over here. There's just the model with 11, of course, because using all of them. Now, in order to select a single best model, we must simply choose among these p plus 1 options, referring to the m0 to mp. This task must be performed with care because the RSS of these p plus 1 models decreases monotonically and r squared increases monotonically as the number of features included in the model increases. Therefore, if we use these statistics meaning RSS or R squared, we will always end up with a model involving all of the variables. The problem is that a low RSS or a high R squared indicates a model with a low training error, whereas we wish to choose a model that has a low test error, right? Therefore, in step 3, we use cross-validated prediction error, CP, which I think we had skipped, BIC, which we had skipped, or adjusted R squared, which we had skipped, in order to select among M0 to MP. These approaches are discussed in section 6.13. An application of best subset selection is shown in figure 6.1. Each plotted point corresponds to a least squares regression model fit using a different subset of the 11 predictors in the credit dataset. Discussed in chapter 3, here the variable ethnicity is a 3-level qualitative variable and so is represented by 2 dummy variables which are selected separately in this case. We have plotted the RSS and R squared statistics for each model as a function of the number of variables. The red curves connect the best models for each model size, so the number of predictors, according to RSS or R squared. The figure shows that, as expected, these quantities improve as the number of variables increases. However, from the 3-variable model on, there is little improvement in RSS or R squared as a result of including additional predictors. So it's basically flat lines over here. Although we have presented best subset selection here for least squares regression, the same ideas apply to other types of models, such as logistic regression. In the case of logistic regression, instead of ordering models by RSS in step 2, we instead use the deviance, a measure that plays the role of RSS for a broader class of models. I don't think this is too important for the time being. The deviance is negative 2 times the maximized log likelihood. The smaller the deviance, the better the fit. While best subset selection is a simple and conceptually appealing approach, it suffers from computational limitations, right? The number of possible models that must be considered grows rapidly as P increases. We get these exponential effects. In general, there are 2 to the P models that involve subsets of P predictors. So if P equals 10, then there are approximately 1,000 possible models to be considered. And if P equals 20, which is not a lot, is it? Then there are over 1 million possibilities. 2 to the power of 20 is going to be more than 1 million. Consequently, right, I mean, yeah, obviously. Consequently, best subset selection becomes computationally infeasible for values of P greater than around 40, even with extremely fast modern computers. There are computational shortcuts, so-called branch and bound techniques for eliminating some choices, but these have their limitations as P gets large. They also only work for least squares linear regression. We present computationally alternatives to best subset selection next. So this was best subsets. So we're doing subset selection. We're doing subset selection where you're removing any predictors that don't really help the predict the response. So we started with one type of subset selection, best subset selection. Now we're going to move on to stepwise selection. For computational reasons, best subset selection cannot be applied with very large P. Best subset selection may also suffer from statistical problems when P is large. The larger the search space, the higher the chance of finding models that look good on the training data, even though they might not have any predictive power on future data. It would just be a coincidence. Thus, an enormous search space can lead to overfitting and high variance of the coefficient estimates. For both of these reasons, stepwise methods, which explore a far more restricted set of models, are attractive alternatives to best subset selection. Okay. I know it's a lot to take in. We're on, believe it or not, now have we done every single page of the book? No, but I think we've easily done between 80 to 85% of the pages until this point. Forward, stepwise, and the book makes learning quite straightforward. Let's be honest. It's definitely not all authors that take such good care of their readership. Forward stepwise selection is a computationally efficient alternative to best subset selection. While the best subset selection procedure considers all 2 to the power of p possible models containing subsets of the p predictors, forward stepwise considers a much smaller set of models. Forward stepwise selection begins with a model containing no predictors. So same as whatever we had earlier. What was it? Best subset selection. And then adds predictors to the model one at a time until all of the predictors are in the model. In particular, at each step, the variable that gives the greatest additional improvement to the fit is added to the model. More formally, the forward stepwise selection procedure is given in this algorithm. Let's see. So again, starting with step 1, you have the null model. The next step, and notice the indexing is different now. We're only going to get to p minus 1. Let's see. Sorry. Consider all p minus k models. P minus k. So let's say k is 0, although we'll probably do this tomorrow, but let's say k is 0. P minus k would just be p. So consider all p models that augment the predictors in mk, so mp, with one additional predictor. This I don't understand. So you have to start with k equals 0. That's probably the worst time to try and understand this algorithm. Though we still have not quite done yet. And try to figure out how to use this app as well. Let's see. Let's just skip this and we'll start with it in the next section. Then there's backwards. So with the backwards algorithm, and let's see, that was page 210. We'll have the Akaki information criterion and the Bayesian here. So it's more of the same, isn't it? Although, okay, this is going to get perhaps quite mathematically intense over here. Although if the initial impression that I've got of this book is anything to go by, when it does do mathematics, it's really when it's when it's totally unavoidable. So there is quite a lot going on over here. We have easily around 50 pages. We've done longer chapters, so let's not lose hope. Then we'll start chapter 7, but maybe that's a bit optimistic to look at chapter 7 from now. Okay, I'm going to stop over here, and when we come back, we'll start by properly understanding this algorithm. this forward stepwise selection. Okay, just going to stop here.